Hello, in this video we're in the multiple linear regression setting, and this is part 2 of studentized residuals. So we have a linear model, x beta plus epsilon, and the assumptions on the epsilon or the error terms are multivariate normal, mean zero, covariance matrix, sigma squared I. Now here we're going to develop a test to test for outliers, but really, so the goal is to detect outliers. Is that data point an outlier or not? But why is it an outlier? One, it could be a mistake, and we're not going to consider that. But the other possibilities for why being an outlier is that there's a shift in the variance somehow. So the epsilon is normally distributed at mean zero, and there's some sort of added variance to it, and that's why it's farther apart from the rest of the data. And the other way to think about it is that it's a mean shift. So this epsilon, instead of being a mean of zero, fluctuating around the line, it's biased in some direction. Same variance, but just a mean shift. And so these are the two things we're going to consider here. Now, a few notes that if the ith observation is an outlier, is this still true? The expected value of s squared, the mean square error, is an unbiased estimator for the population variance. Now, when all the model assumptions are true, this is true. But if the ith observation, doesn't follow the model assumptions, then the answer to this is no. That's not an unbiased estimate. And in part 1, previous video 65 in this playlist, which is part 1 of the studentized residuals, the playlist is Generalized Linear Models Regression. We showed that s squared is inflated when that ith observation is an outlier. So one solution is to use all the data except for the ith observation to estimate, to calculate s squared. As we use that as an estimate for sigma squared, right? We just get rid of that observation. And that means to remove the ith observation and then estimate sigma squared with s squared minus I. So the ith observation removed. So the number of data points is n minus 1 minus k plus 1, but that can just be called n minus k plus 2. And we're going to sum through all observations except for the ith one. We're going to take the data point minus the fitted line, but the fit is without that ith observation, and that's it. So that's our estimate for the population variance. And that seems very intuitive to me to use, and that's what we do. So in the first test, well, let's keep going here. So to develop a test to detect an outlier, the possible null and alternative hypothesis are these, and it ends up the same test is good for both of them. So there's either a no mean shift or a mean shift in the error term, or there's a no increase in variance, or we have an increase in variance, in that outlier. So the statistic is called the R student statistic, and actually there's a function in R called R student. It's in base R, and it's used in linear models. So look that up, R student. And this one here is called the externalized the externalized studentized residual, or simply just R student. So here's the statistic. Now in part 1, in this formula, we used S instead of S minus I, and we called it R. And RI is called the internal studentized residual. And that's because the estimate of the population variance used the ith observation when we're looking at the ith residual. So it's sort of internalized estimate. And externalized means we didn't use that ith observation when we're looking at the ith residual. yeah, so this is the test statistic, and we will show that indeed follows a t-distribution. Okay, so the rejection region is, it's a two-sided test, so the t-test, so rejection region over here, and if it's in too low or too high, we reject. But another way to think about it is that if the absolute value of the test statistic is greater than the cutoff, and since it's two-tailed, that should be divided by 2, we reject. Now, we want to prove that TI follows a t-distribution. And we're going to go through notes here. So note 1 is from previous video 49 and 65. We showed that the ith residual, which is this, follows a normal distribution. And if we standardize it, so divided by the standard deviation, it's a standard normal distribution. Then the ith, so the estimate of the population variance without the ith observation is this, and this right here is the sum of squared error minus the ith observation. And we can write that in matrix form like this, where this is the hat matrix minus ith observation, this is the y vector minus ith observation. And in previous video 27, we show how to derive these calculations, to put in scalar notation to go to matrix notation. Now granted, there we used all observations, so if you take that away, then this can be written like this, take the minus I, and but it's the same derivation. So this is the identity matrix minus the hat matrix minus that ith observation. Now from previous video 24 and previous video 27, we showed that this sum of squared error divided by the population variance is a central chi-squared with n minus k plus 2 degrees of freedom, because that's what it takes to make this unbiased. The fitted value minus that observation, so this is the fitted model, is really the it's the hat matrix times the y vector. So that should be the data, not the fitted value. And actually that's why they call it the hat matrix. So if you multiply the hat matrix times y, it puts a hat on it. That's the hat matrix. So this is the fitted model without observation I. Now, I have a video called Independence of Quadratic Forms, where we show if we have two variables that are linear in the y, so this one and this one, so this is a quadratic form in the y's. We showed, and the y's are normally distributed, so that's also important, that if this matrix times this matrix is 0, then this quantity is independent of this quantity. And so from this video, these two are independent since the product of these are 0. Remember, the hat matrix times itself is the hat matrix. The identity times the hat matrix is the hat matrix. So you got the hat matrix minus the hat matrix. Well, that's 0. So there it proves that this quantity and the sum of squared errors is independent. So now point 6. Now, by assumption, all the data points are independent. So yi is independent of all the other data points that isn't y, right? So that means that this yi, the ith data point, is independent of SSE, the sum squared errors, minus the ith data point, because in here we didn't use the ith data point. So it has to be independent of I. And functions of data, functions of independent data are independent. So this is independent of the ith observation. Okay, so from previous video 65, or part 1, that if we look at the residual, we called it EI, there was a formula that put it in terms of the press residual. And I'll let you look at this. This is basically a leave one out predicted error sum of squares. And this is the hat matrix, the diagonal of the hat matrix. But this right here means you take the ith data point and you use the fitted model that didn't use the ith observation, and you try to predict the ith observation. That's what the press residual does. So this can be written in terms of this. Now, the ith residual is independent of the sum squared errors, right? Because sum squared errors is independent of this model here. We just showed that in part 5. And of course, SSE minus I doesn't even use the ith observation, so it has to be independent of this. But this is the ith residual. So the ith residual is independent of the sum squared error that minus the ith observation. So that's from parts 5 and 6, right? Now let's look at the test statistic. So if you have a normal distribution over the square root of a chi-squared divided by its degrees of freedom, that is a t-distribution, well, assuming the numerator and denominator are independent. So we'll hold off on that a second. So we showed that this is a standard normal distribution, and SSE divided by the population variance, that's a chi-squared. Its degrees of freedom was n minus k plus 2, and all this reduces to this, okay, which is the test statistic. Now notice the only random variable here is SSE, and the only random variable here is this and that. And this is independent of that and independent of that, so the numerator and denominator are independent. So this, which is TI, which we called it on page 1, is a central chi-squared, or central t-distribution with n minus k plus 2 degrees of freedom. Now, a few notes here. This test is for one outlier at a time, and care should be taken for simultaneous testing of all observations. Okay, so what that means is if you're conducting an experiment and for some reason maybe the equipment goes wrong on one observation, you're like, oh, maybe, you know, we got to test to see if that ends up being an outlier, that observation. Well, then this test is the case for that. But if you're going to use this test and say, you know, you're going to sort all the residuals and look for the largest and then use this test, you're essentially doing a test on every residual, right? And so it's not really testing the largest, you know, residual is not appropriate because you're sort of inherently doing tests on all of them. And so, but one approach, and I actually like this approach, is a Bonferroni approach can be used with the new alpha over n significance level. And it ends up not being that extreme or that conservative. And it's a pretty nice test that you can put this t, the cutoff region at t sub alpha divided by n, and instead of being a cutoff of like 3 or whatever it ends up, it's like 4 or 5. So it's a little bit bigger, but you're protected and you can do all the tests on all the residuals. Anyway, I like that approach, by the way. Now, there are tests for testing groups of observations as outliers. So, you know, are these 4 outliers, or these 6, or these 2, and the approach is you set up indicator variables for the ones that you think are outliers, you know, to distinguish as possible outliers. I've personally never used this test, and caution is definitely warranted when you're doing tests like this on groups of observations of outliers. But I'm going to leave that to the reviewer to investigate. Now, essentially, this talk would have been finished, but I later went back and made this to a 4. Used to be a 3 pages. And I decided to put, or to derive the power of this test, because I actually think it helps to understand what's going on with this test. And that's the externalized studentized residual. So the power for this test, and this is the last page, is the null hypothesis is there's no mean shift versus that there is a mean shift in that residual. So basically the ith residual follows this. It's normal with some mean and variance, sigma squared, and all the other residuals are normally distributed, mean zero, and variance sigma squared. Now the power is that the test statistic falls in the rejection region, given that that it should, that the alternative is true. So that means we need to figure out the distribution under the alternative region. And so let's derive that. So as a reminder, if we let Zi be this quantity here, now remember the test Ti has the Si minus 1 here, the estimate of this without the ith observation. But this follows a standard normal distribution. We're going to call it Zi. So the test statistic is Z minus its expected value divided by this. Now this is a chi-square distribution, and this is a standard normal. Now under the null hypothesis, well, let's stop there for a second. So this is standard normal. This is the square root of a chi-square distribution divided by its degrees of freedom. And this minus piece, that's the non-centrality parameter. So this test statistic, Ti, follows a non-central t-distribution with degrees of freedom, df. And it has non-centrality parameters in C3, non-centrality parameter. So under the null hypothesis, this expected value, which is this expected value, the expected value of the residual is 0, right? And so it's a central. But under the null, that it is not, the non-centrality parameter is not 0. So note that using all observations is a violation on the model assumptions. That means if we use all the observations and calculate the least squares estimate of beta, it is not unbiased. It's a biased estimate, and that's because the ith observation violates the assumptions, right? The expected value of the ith observation is the model value plus delta I, right? That was the assumption under the null or alternative hypothesis, right? So we have to be careful, and we can't use all the data to estimate beta, right? But if we leave out that ith observation and then estimate beta, it is an unbiased estimate for beta. So, and what I'm saying is, so if we look at the expected value of the fitted model without the ith observation, that's saying it's the ith row times the least squares estimate of the beta minus that ith observation. This is unbiased because all the data follow the model assumptions. So it is this. So we have this as this, and the expected value of that fit is this. So and remember, we're looking at the non-centrality parameter here, which is the expected value of this. So if we look at the expected value of this, now by this video in part 1, we showed that the error, well, actually, this piece here can be written like this, where that's the ith observation, and that's the fitted model without the ith observation, right? So then this expected value, since that's constant comes out, that's constant comes out, and the expected value of yi is this. The expected value of the fitted model is this, so it's the difference. So that cancels with that, and we're left with this delta. So it's the shift in that residual. And so that's the non-centrality parameter. And that's it. So to calculate power, you have to plug this in for that. And all this, and so, and to calculate power or sample size, you have to assume certain, you have to assume values for the population parameters. But the interesting note here is that the non-centrality parameter decreases as HI goes to 1, right? So as the data points or the X values, if it's influential, this non-centrality parameter decreases. So thus the power decreases. The power function of a non-central T distribution is actually monotonic in the non-centrality parameter. So if everything's held fixed and you decrease the non-centrality parameter, power decreases. If you increase it, power increases. And I actually have a nice article illustrating and calculating sample size for what's called Fullman's test. Just published it, by the way. But so anyway, so I just thought that was kind of interesting, that if the data point is more towards the center of the data, then you have more power to conduct this test. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.